So during this lab, we started with a more complex design, and as we started to kind of analyze what we needed to change and how we could improve on the previous lab designs, we realized that our initial design for this lab was a bit too complex, and I'll show why and the reasons why we could have easily fixed it using just adding more weight to a previous design. So basically, we initially planned to use two separate designs, which were two of the designs were actually used by the previous lab groups, but we wanted to combine both, so we were going to have a rack and pawl design, and then also a spinning ratchet design that would be powered by the moving rack. So basically, we realized that for the last group that used the rack and pawl design, they had a limit as to how much work they could produce over a time span, because it was limited by the length of the rack itself and how much you could change, or how high you could raise the rack. And what we wanted to do was create a rack that would raise to the top, and then by a series of two slots in which the pawls would engage into, the rack itself would drop back down once it reached the top. And so here I have an image. It's a pretty rough sketch. You'll see that there's two slots that the pawls can engage into. So the inner slot here would be the slot that when the pawls are engaged in this slot, they would be engaged with the teeth of the rack, and so it would produce upwards movement. And then once the rack itself reached the top, we would have a secondary slot with a flap at the bottom. So here it would move over to the secondary smooth outer slot via this one-way flap, and once it engaged into the second slot, the pawls would no longer be making contact with the teeth of the rack, allowing for just it would simply slide down. The entire rack itself would slide down, and at the top of the outer slot, you'll see that it is angled so that the pawls themselves would be forced to move back into the inner the inner slot. Then once they're moved back into the inner slot and re-engaged with the teeth of the rack, the cycle would continue, and the rack itself would be moved back up, so we would have a continuous up and down process of the rack. This continuous up and down process would continuously be rotating this ratchet design, that as the rack is lifted, the ratchet spins in one direction, not allowing for movement in the other direction, and thus we would have continuous movement or spinning of the ratchet, and the ratchet itself would be spinning to lift a weight. So while this design seemed like it would be a rather good fix to a problem we spotted, we realized that it was a very time-consuming design, and it would be it'd be very hard to make. And on top of that, it would with all the moving parts and different mechanisms, there'd be a lot of friction, and with the added friction, we'd have a lot of work lost.
So with the idea that we would be losing a lot of work due to these extra pieces and the added friction of these extra pieces, we realized a much more efficient and simpler design change that would have fixed the problem of the rack bottoming out is to just simply add extra weight to the bottom of our rack that we're lifting. And with that, we would be slowing down each cycle of the piston, and we would, with the ideal amount of weight, we would be able to finish the 5-minute test demo with our rack moving the entire time. So we wouldn't bottom out until the very end of the cycle, or until the very end of the 5-minute time period, and then we wouldn't have to worry about making a rack that would go up and down.
In order to calculate the work per cycle of the piston system, we had to first calculate how much force was actually being applied by the piston during each cycle. So we knew how much force the thing actually weighed. It was 0.194 grams of weight that was added to a 100 gram rack. So if we looked at the actual arm of the device, you could take a moment around the pin, and based on the moment, we could calculate how much the force of the piston was compared to the force of the weight if it actually lifted the entire thing to capacity. Then, based on that force, we can find the delta P for the PV diagram, which would be P2 minus P1, which would remove all the atmospheric pressure. So it would just be the force of the piston divided by the area of the piston, which gave us a delta P of 463.381 pascals. Then we also have to calculate the delta V. So V3 minus V2 would include the volume of the tube with air and the volume of the canister. It would only really include the difference in volume of the piston itself. So then a piston displaced 10 centimeters, which is 0.1 meters, and then this would be the area of the piston itself. So that would give us the total displacement of volume, which was 0.00023203 meters cubed. So that would give us this PV diagram. And on the left is the difference in pressure. And you can see from 1 to 2, only the pressure is increasing. Then the volume begins to increase from 2 to 3. Once it overcomes the weight of the whole system. And then from 3 to 4, it starts cooling down and the pressure decreases. And then from 4 to 1, the volume will decrease afterwards. So in order to find the work of the piston per cycle, it's the area under this curve. So it would be the delta P times the delta V. And the work of the piston ended up being 0.094 joules per cycle. So then, once we had the work of the piston, we knew that the total length of our rack itself was 18 inches. And we knew ideally that if the piston moved completely up, it would move the rack up 1.75 inches. So hypothetically, ideally, if the piston moved all the way up each time, it would take 10.3 cycles in total. But based on the amount of joules that we calculated previously, for 18 inches, which would be 0.45 meters, with that amount of joules per cycle, it would take around 14 cycles to make it all the way through our rack. But in actuality, we only moved 15 inches up, which was 0.381 meters, and divided by the amount of joules we had, ideally it would be 11.2 cycles also. So the reasons that it didn't hit the expected performance that we had hoped for, one of the reasons is that we attached the actual arm itself by a string to the top of the piston, and the string was loose enough so that it could get max height, but because it was so loose, it didn't start pulling down to get the other side to move up as nicely from the beginning. So we lost a lot of the work on the way back while the piston was, the volume was decreasing. We lost a lot of that work on the way down, which was included in the work of the cycle. So we actually had less work per cycle than we had originally calculated. Also, the temperatures of the actual baths themselves weren't staying at the same temperature the whole time. They were cooling down as the process was going on, especially since a really cold canister would be placed in a really hot, warm bath and it would cool down the temperature. Also, one of the problems could be caused here as there's friction with the metal pieces that we had to keep the tube in place. And that friction could cause a massive loss of work, especially because every single time it has to move up, it would rub against the metal bar. And then finally, one of the reasons for deviation could be because there was some wiggle room on the sides. Therefore, the arms didn't always necessarily line up with the rack, and it might not have moved up as smoothly as we'd hoped. The friction also would attribute to the fact that not all the work would be contributed to potential energy, which would actually lower the amount that the rack was raised.
There are a couple of things we could have done to improve our engine. First of all, we could have used rubber bands to connect the piston with our engine that allowed us to take full advantage of all the piston's travel. The rubber band would allow the piston head to reach max height while also pull the arm down on the second half of the cycle. The string we used was a better solution than a rigid mounting. However, it became less and less effective as it unraveled, leaving us with long periods of time where no work was produced. Second, we could have reduced friction in our system that would have increased our work output. We sanded some of the components before testing to help out, but adding some form of lubrication would have also reduced friction.